What's up, guys? Welcome back to my channel. So today we're going to do a fun calculus problem that usually don't even won't even show up on a calculus textbook nor in a calculus course. And what I meant is high school calculus or first year of calculus course. Of course, we have the integral of x to dx. I'm just kidding. This, of course, everyone should have already known what the answer is, especially if you have already taken or isn't taking a first calculus course, regardless if you're in high school or in college. Okay, as long as you understand what antiderivative is, and again, I actually prefer the term antiderivative more than just integral because a couple of reasons. When I say integral, I usually would think of taking the area of or more like a measure of some kind of functions. But when I say antiderivative, it's just giving me a concept that I'm just trying to find out the inverse. Let's see, how should I say it? It's more kind of like an inverse operation of derivative. So anyway, as long as you're already in the second half of the first course of calculus, you probably have already started learning what antiderivative is, as well as knowing how to take a derivative of any power functions. So it should not be any problem for you guys to figure out what the integral of x dx is. So what are we supposed to do? Today we're actually going to try to find out the antiderivative of the floor function. In this case, it will be the floor of x to dx. And here right now we are going to just look at the floor of the linear function here, as we usually would just like to start off with basic. So how are we supposed to find the general expression of it? And again, if we're actually thinking of a definite integral, it means that we are going to have a lower limit and an upper limit, and it will be kind of easy for us to figure out because we just need to look at the graph of this given function, and we can actually try to use other kinds of methods than just calculus to give us the results that we actually want. We can kind of use like a geometry or high school geometry trick of cutting off the shape into certain triangles or rectangles or trapezoids, however we want, and we actually know the formulas of finding the areas of those shapes, so that we can just figure out the area of each part and then add them all back up to get a numerical result, right? But this time, we actually have the antiderivative, meaning that there's no numbers, no lower limit, no upper limit, and we actually wouldn't be able to simply use the graph to help us finding it without avoiding any calculus parts that we actually need. So let's jump into the solution. So first, we actually need to use the concept of fundamental theorem of calculus, which says that we can first call this integral, let's say I, and then we'll rewrite the integral as following. Instead of calling x, we're going to use a dummy variable to replace it. So in this case, I'm going to use u, because why not? U sub, right? And then now we're going to use the second part of fundamental, well, actually it's the first part. I think it's the first part of the fundamental theorem of calculus, which says that this function here, if we call it f of x with a capital F, which is actually the integral, it can be rewritten as the integral from 0 to the x value here. Well, usually they will say f of a, and then it will be from 0 to a. Again, just because we want to throw the x back in later on, I'll just stick it with x of the yeah, the derivative of this capital function, which is actually the function that's given here, okay? And then we'll be able to find the we were able to define this integral here, such that the derivative of this function here will then be will just be the function itself by substituting in the variable that we have. And of course, if this x is replaced by other values such as 2x, 3x, or even x squared or other kinds of stuff, we have to use a chain rule. And don't forget, we need to use a chain rule of taking the derivative of this part and then multiply and try to end up the conclusion there. But anyway, with this idea, we now can actually try to figure out what this integral is. So first, we need to recall what the floor function will look like. So let's take a look at the graph on the right hand side, and maybe I should actually extend a little bit. Okay, so here we'll have the x value, we'll have the y value here. Then for the floor function, y equals the floor of x, or we will say the round down of x. It will be defined this way. It is actually equal to the n value, which is an integer. Yeah, such that n is an integer, and n is the maximum. Is the maximum integer that is less than or equal to the x value that we have. So graphically, this is what we will have. From 0 to 1, if we choose the x value between 0 to 1, not including 1, we actually have the y value equals to 0. So in other words, we are just having any number, and then we will just take away all the decimal parts. Okay, so let's say if we have 0.5, we'll take away everything after the decimal point, and then just keep the whole number part or the integer part. This is pretty much what the floor function is going to tell us. Then between 1 to 2, we actually have the y value is equal to 1, because in decimal it will always be treated as 1 point some numbers. Then of course, if we cut off at the decimal point, we will just have the one part in the integer. So we will just say that that will be our y value. So if we do it on the other way, we'll actually get from -1 to 1, we'll actually have the value is always equal to -1. And again, this is a little bit strange because we cannot just simply think as a cutoff. We need to go back to the definition that since for any numbers between -1 to 0, it is actually bigger than -1, but always less than 0. So we cannot choose 0. And since the output has to be an integer, the highest value that we can choose is -1. Okay, so we'll list one more here, -2. So this is how the graph will actually look like. Let's say here is from 2 to 3, and then from 3 to 4 will be something like this. All right, so here is the function, where the graph of the function y equals the floor of x. Then what can we actually do now? Well, if we think of this interval here, let's pretend that x is greater than 0. Of course, when x is less than 0, we just need to flip the sign. But if we try to keep it simple, pretend that x is greater than 0, then by the definition of the floor function, we actually have something that's actually cutting off for this here. We know that there exists an integer such that x has to be greater than or equal to such integer where that integer is the biggest integer that can satisfy this condition. So in other words, we'll be able to get the floor of x no matter what. Then by the second law of fundamental theorem of calculus, we can divide up an interval into two parts where the break off will just be not u. Here is x. The break off point would just be the upper bound of the first half and the lower bound of the second half. So in this case, we actually will say that if we are actually starting from 0 to x, we know that the floor of x has to be lying between 0 and x, such that we'll actually make a cutoff at the floor of x to divide up into two parts. Now, for the first interval here, notice that 0 is of course an integer, where the floor of x is by definition is also an integer. So if we look at the graph here, we actually have the following. Here we can actually divide up into the sum of, well, let me put it this way. We can actually divide into 0 to 1. Suppose that, assume that floor of x is some value that's actually large. We can just generalize it anyway. So we'll actually get this something very similar from 0 to 1 plus 1 to 2, and then go all the way to the floor of x minus 1 to the floor of x itself. For these intervals, for this interval here, we can actually divide into x amount of intervals, such that now if we look at this graphically, we see that within each interval, each small interval here is always a constant. So in this case, here we will actually have 0. Here is 1, here is 2, so on and so forth, until here we'll actually get x minus 1. And then what is the width of this interval? Now think it geometrically. On this graph, we will say that for each small interval, we actually can form a square, or of course, generally speaking, a rectangle, so that in fact, the integral of each small interval would just be the area of the corresponding rectangle. So in this case, we actually have 0 plus 1 plus 2 plus all the way up to the floor of x minus the floor of x minus 1. So in this case, let me put a parentheses here to refer that this is the last term. So in this case, we actually know what the interval from 0 to the floor of x of the function floor of u du in terms of x, of course. Good. So now we still have the second part, which is from the floor of x to x itself. So based on the graph and our observation of all previous terms, we actually get that the height of that rectangle would just be the lower bound or the floor of x. And then what about the width? The width is, of course, since it's a constant, it would just be the upper bound minus the lower bound. So we will have x minus floor of x. Good. So now we actually finished the second part, and we can actually just put them together like this. And here we go. We're going to continue on this on the next board and finish up the rest of the problem. So in the end of the last board, we actually found out by dividing up the interval into two big parts, where the first part is actually going to be chopped up by many different small intervals to obtain the following expression here. And now we're just trying to finalize and trying to simplify the expression. Well, notice that on the first brackets here, every single term is in fact an integer. And again, even the very last term, the floor of x minus 1 is an integer, because by definition, the floor function is going to give us an output of an integer. Then minus 1 is still an integer. So in fact, we actually get all the integers, and we actually get an arithmetic sum here from 0 all the way to the very last term. So we can just use the sum of the linear terms to actually give us the total sum here will be the first term plus the last term times the number of terms that we have. Well, since we're actually starting from 0, instead of having the floor of x minus 1 terms, we actually need to add one more term here. So in fact, we actually have the floor of x many terms, and then all divided by 2. Okay, then we will just add the second part, which is in fact just the floor of x times the quantity x minus the floor of x. And why do I not try to multiply it? Because in fact, we will be able to factor so that it will be easier, and we can rewrite the expression more neatly. Then in this case, we actually have the common factor, the floor of x and 2 in the denominator. So we will actually factor out the floor of x over 2, such that now for the first term we have 0 plus everything inside the parentheses, which is just the stuff in the parentheses. Okay, plus we have everything inside the parentheses times 2 as we factor out our half out, so that we actually get plus 2 times everything inside of parentheses. And now don't forget, we actually need to put brackets here. And now we just need to simplify everything in the bracket and obtain that. In fact, we can actually write as 1/2 times this times, well, we actually have 2 times x here, so we get 2x. And then let's see, we have one copy of floor of x, or just simply call the floor from now, plus 2 times negative floor, which gives us negative 2 copies. So we have 1 minus 2 to end up with negative 1 copy of the floor function. And finally, we have the minus 1 here to end up our expression. So here is going to give us what the expression would look like for the floor function of u and du if we are starting from 0 to some x value. So now, as we try to find out the antiderivative of the function, don't forget, since it is not a definite integral or even some indefinite integral with some certain bound there, since there is no upper bound, lower bound at all, we always need to add the constant term, as how we learned in the first class of taking integral. Okay, so our final answer for this problem here, the integral of the floor function of x in dx is in fact equal to 1/2 times the floor of x times the quantity 2x minus the floor of x minus 1 plus some constant c here. And here, let me erase in here the purple part so that we're not going to get misunderstood. And this will be the general expression of the floor function of x in dx as we try to take the integral of it. Good. So, of course, you might ask, how do we know that if it's true? Well, there are a few values that you can actually try to substitute in, but as the video is kind of too long, I'll just leave it as an assignment for you guys. Here are the 3 different sets of values that you can actually try. First one, based on the graph, we know that if we take the x line between 0 to 1, and you can actually include 1 as well, because even if we include 1, the area parts will actually not going to change because of the singleton. Anyway, you can try to check what happened when x is lying between 0 and 1, and this should yield the answer of such integral is going to turn into 0. Well, if we ignore the c part, this part is supposed to turn into 0. So let me just say it this way: the integral is going to turn into 0. And then if we choose between 1 to 2, you should actually get the integral, the expression of this integral to be simplified down to just x minus 1 value. Okay, last but not least, you can try to set x into any integers, and then use two different methods by setting up as x equals some integer n and x equals some integer n minus 1, and then see if you substitute it onto the right hand side, let's see if you'll be able to get the same result using the two different values, n and n minus 1. Okay, that's it. Hopefully you all enjoyed this video. Don't forget to subscribe and like this video if you actually do. Also, turn on the notifications so that whenever I have new videos, you will not miss it. And if you have any thoughts, you can leave your comment down below. I'll see you guys in the next video.